All right, very apropos that we have our panel on big data, little water. We just heard about big data, big water, and I think it's an excellent way to launch into a very rich afternoon of conversation. Among those things, you may remember we're doing these lightning talks at 4:30. I noticed 4 of you have signed up so far, which is great. You'll each get 3 minutes plus 2 minutes of questions to you right after that. There's room for more, so don't be shy when you go out to grab a cup of coffee or check your email or whatever it is. Just look around the corner out in the lobby and sign up for those if you would. We want to make sure that the Q&As are great. We encourage that, but also if you have something on your mind and you want to make a statement or comment on something you saw or do some reflection, recommend a new research project for Joel Baker and John Stark, anything like that. Funding for them, they like to hear about that stuff. You can bring that to bear during the 3-minute lightning talks coming up later this afternoon. I'm going to follow the same pattern. I'm going to introduce the moderator for the next panel, and then he'll introduce or have the panelists introduce themselves and then launch into their presentations, followed by Q&A. Scott McQueen is the Chief Strategy Office for Geoengineers. Geo is one of our sponsors here today, so we appreciate that. He has over 20 years of leadership experience designing, developing, and implementing software solutions for top-tier commercial companies, government agencies, and research institutes around the world. Some of his clients include, and this is not a complete list, but some of them include the Nature Conservancy, Plum Creek Timber, Potlatch, Rayonier, Union Pacific Railroad, and several state government departments. So another great example of someone who's worked deeply in the private sector and also with public sector clients. So with that, Scott, why don't you and your panel come forward, and we'll get things rolling. Thank you. Let's welcome the panel. Thank you.
Thank you. So we're going to change things up a little bit while the panel's getting seated. Everyone 50 and under, stand up. 50 and under, stand up. And by the way, I'd be sitting down right now, so that just dated me. 40 and under, stay standing up. 30 and under, stay standing up. How about my 2 guys over here, Andrew and Justin? This is our next generation. The rest of us are aging pipes, I think is what one of the terms was. So how are we going to reach out to them and engage them more, and especially around this idea of innovation and technology? So keep that in mind. And I want a lot of questions from that 30 and under crowd. So there, did I set the stage? My first speaker, his name is Faisal Hossain. And Faisal received his PhD from the University of Connecticut in 2004 and a master's and a BS from the National University of Singapore. He is currently an associate professor in the Department of Civil and Environmental Engineering at the University of Washington. His research interests are hydrologic remote sensing, human impacts of weather and climate, sustainable water resources management, and he's also the recipient of awards such as the NASA Earth Systems Science Fellowship, NASA New Investigator Award, U.S. Fulbright Faculty Award, and American Geophysical Union Charles Falkenberg Award. So Faisal is going to give us starting probably at a world perspective, and then we're going to kind of go down into more regional perspectives as we kind of move down the panel here. So with that, Faisal, do you want to come up?
Where's the
All right,
Well, good afternoon, and thank you for this great opportunity to be given a chance. So just prior to my talk, my very esteemed colleague Kristen laid down the foundation to what I would call a very excellent topic. And she focused mostly on the U.S. So I would like to kind of take you folks on a journey on anything but the U.S., the non-U.S. regions where, that other 5 or 6 billion people of this universe where, water is still important there as well. But the challenges we face are a little different. So I kept with the title, Big Data, Little Water, but with the caveat that, I want to focus on little water information, which which comes in the way of empowerment. So empowerment is really the buzzword that would like to talk about. So let's take a look at some pictures. I'm a little biased towards water quantity issues, but water has two aspects to it: how it's moving, the flux, where, how much, and the quality aspect too, which is not something that we focus a lot on. But if you just focus on the water quantity aspect, most of the water issues, you could break it down into this simple problem, which is how much water do we will have, where, and when. And you probably might know in 2004, the Office of Science at White House, they commissioned a study of the water resources of the United States. I think 40 water scientists took part just to find out the answer to how much water does the U.S. have. And the answer that they came up with after a year of study was, we don't know. And a lot of it goes into the issues that I'll talk about today. But on the slide that you see some interesting pictures, profound, but I'm showing you two that are 1 month apart in the South Asian region. This railway bridge that you see, this is on the river Ganges, and just a month apart, you see the drastic difference. Now, this bridge has been around for 150 years. The British engineers built it, and back in like a century ago, it wasn't like this. You had the river full of water, and the poets would write about it in their poems, but nowadays the poets write about the rivers not having water anymore, because the issue is you have some human impoundment upstream by another nation due to increasing water demand, and it creates such extreme situations just in a space of a month. There's another one where it's an example of poor urban water management. This just happened in a manner of, I think, a 1 hour storm caused it. Just very rapidly, bad urban storm sewer systems, detention ponds, and all that. Down below, I lived through this because I was living in Nashville when this happened. This happened, I think, the same time as the Deepwater Horizon happened, but I think this kind of did not come into the limelight for a lot of reasons. But you might know the story of this, which is one of the largest dam east of the Mississippi River, which is the Wolf Creek Dam. It was operating at minimum pool, and because of that very reason, when they were struck with a very extreme precipitation event, what we call an atmospheric river event, which is very common in the Northwest, but also happens sometimes in the Southeast as well, they kept passing all the waters further downstream, and a combination of runoff, extreme precip patterns, and management caused the city to flood. And the other things you see is this is more on the water supply needs. You see the contrast. You see drought in progress. So one thing that's kind of very apparent here is, you've all heard of the term called Anthropocene. So I think we're living in the Anthropocene for surface water, whether we realize it or not. Even when it comes down to the smallest river basins, it's very hard to find a single river basin that's not impacted by human regulation. There's some sort of a human fingerprint that messes up the way the water is going to move, how, where, and when, right? So to get to the bottom of that answer, like, how do we answer this question? How much water will we have, where, and when? I think you can break it down into simple, components. You would need to have a way to crunch out the numbers like a model, so a computational modeling framework, and Christine talked about that in a fantastic way. And that modeling framework would need to be fed or forced or constrained by a lot of data that's coming in on the boundary conditions of the water. So you solve it that way to kind of get to the point where you can predict where water is and what form at X, Y, Z, and T. So we can kind of call it a data modeling approach. So the data is the big data part, and the model is the modeling part. However, there are challenges to this, especially if you step outside the U.S. and the developed world. It was great to see the era that we're headed to in the U.S., the National Water Center, and then the stuff that Professor David Maitman is doing with Microsoft Research, it's all fantastic. But when you go into the vast regions of the developing world, and even maybe to some extent also in the developed world in some cases, you face some curses or challenges. I like to call them the four curses. In the interest of time, I won't talk about all of them. Maybe I'll just show you an example of the infrastructural curse, which I think has some relevance to the U.S. as well. Although my favorite is the human resources challenge, which is, how do you keep up with the scientific state of art where we, being in the academia or in the scientific world, can make ourselves redundant and go play golf so that the industry or the practicing world can take care of it. That's something that we're still figuring out, especially in a lot of fields. But you have these four curses. One is political, and you'll be surprised. It's not just sharing the water, it's also sharing the water information, which there's a term for it, hydropolitics, actually. At Oregon State, Aaron Wolf came up with it about 15 years ago. And a lot of people do studies on it, and it's very widespread in the developing world. So it's on issues of turf and agencies being very protective and nations, because it's a national security risk to share information. Infrastructure is, of course, coming to the economic. I think you understand that if we're going to measure water the conventional way that you and I are used to using probes on the ground, there is a cost associated with it. And human resources is what I just talked about, is, how do we kind of make sure the forest blooms in a way that we can step back and go do our own thing, and the world kind of sort of takes care of itself and things run on its own. So on the infrastructural challenge, I just would show you a couple of figures. The thing on your upper right, it's a map of precipitation gauges on the ground, the coverage we have. And wherever you don't see any colored region is basically you have voids there. Well, first of all, it's not really raining a lot in those regions, like the Sahara, North Africa. But the other thing you will notice is that the color code represents basically like the number of gauges you have in a fairly large area, which is about 1,000 square kilometers. So you're talking about maybe 3, 4, 5 gauges, which, as we know from the World Meteorological Organization, is very inadequate. You should have more gauges for that area, just to capture how the rainfalls vary. If you go a little down below, this is from the Global Runoff Data Center, which is a freely available archive of getting information on stream flow or surface water. And what these colors represent to you is anywhere where you don't see blue indicates that the last time those locations where the flow was measured in the river was updated either in the 1980s or before. So there hasn't been any new data added to it. Could be due to a number of reasons. Either the monitoring protocol was taken out, the gauge was taken out, lack of economic resources, all that. So you see a lot of yellow and red. The U.S. is in a much better shape, and so is Japan, and Europe is a little bit better. This figure on the upper left is interesting. It basically shows you, whichever way you want to look at it, left or right, your y-axis is the timeline. So you're kind of going from 1910 to 2010 upwards. And left or right shows you the number of instruments or gauges we have been using to create our global stream flow records. And you will see that we kind of peaked in the 1980s to 90s. Ever since, we've been going down. And that is kind of, in many ways, the sad reality, because that's the conventional way we measure record data for water. And this is from the USGS, a classic figure that shows, the number of USGS stations with 30 or more years of data that's being decommissioned every year. There seems to be sort of an upward spiral. There are a number of reasons behind it that we won't go into. So you get the idea that we are kind of facing a situation where networks are declining, and which is very critical. If you're a hydrologic engineer and you want to do hydrologic design or risk assessment or something, say in the Congo River Basin, you need to have a good set of data, 20, 30, 40 years to look into the trends, do some flood frequency analysis, whatever, but you need to really start with some data. And a lot of the places, if you were to have projects going on, it might be pretty difficult for us to get a handle on what's been going on since the 1980s. So what do we do about it? Can space be the answer to that data part of the data model problem? Probably. So this is where we come in and we try to address it. So this picture is taken from NASA. It's called the A train of satellites. It's basically a bunch of satellites that NASA put into orbit. These are all Earth observing satellites, and in this particular case, it's something I think, very smart. What they did is they put them in such an orbit that one would follow the other in a span of a few seconds to minutes, but each one measures something different. So it could be water vapor, it could be atmospheric chemistry, it could be temperature, it could be something on the ground. So in one location, you get a kind of a very holistic assessment of what's going on. So that was done purely for science. But the point I'm making is there were a lot of platforms out there that uses the Space-borne platform satellites and does remote sensing and can tell us quite a bit on what's really going on with the water and where we have the water, in what form and how much. We've kind of come a fairly significant way. Just to give you an example, this is a very interesting decade, the 2010 to 2020, because ever since the first environmental satellite that was launched, I think it was 1965 or something, TIROS, the first precipitation measuring satellite was launched in the late 70s. We've had a few decades of research done on this to the point that we are now seeing more and more sensors being launched that are dedicated just for water alone, just to get a handle on what's going on the water, on the surface, right? So you have a mission that was launched in February called GPM, Global Precipitation Measurement Mission. It's a multinational mission. It's a great success for international collaboration. NASA banded up with Japanese, Indian, European space agencies. And the goal is to provide precipitation information anywhere on Earth every 3 hours at scales of 10 by 10 kilometers. Sorry, not every 3 hours, every hour. And the data product should be available sometime soon. So it's a big quantum leap from what we were used to. Now we can talk about a lot of operational stuff, a lot of day-to-day stuff that we couldn't do in parts where data was missing. There's this mission coming up on, the wetness of the soil. SMAP, which is being launched, I think, early next year. And, of course, the U.S. Army has a great interest in it, and so do a lot of other people. But the whole idea is to get a handle on whether the soil, the upper 5 to 10 centimeters, is in a drying or a wetting kind of phase, so that you can use that information for crop management, irrigation scheduling, or, even to decide whether you're going to deploy track-mounted or wheel-mounted vehicles. This one that we're on the science team of, called SWOT, doesn't stand for Strengths, Weaknesses, Opportunities, or Threats. It stands for Surface Water Ocean Topography Mission. This is the first dedicated mission for hydrologists like us. It will be launched in 2019 or 20. It's a French NASA mission. And the idea is to provide water surface elevation of water bodies and rivers, using which you can get to the bottom of reservoir storage changes or discharge for major rivers every 7 to 14 days anywhere. And all of this data will be made free. That's a good thing about it. And there's actually more that you'd be surprised that kind of builds on the heritage of research that's been going on since the early 1990s, where they've kind of become fairly stable, mature technology. So one thing that we're seeing a lot of is called altimeters, that you might have heard of, just to measure the altitude. Satellites can do the same thing to give you a handle on how high or low the water surface is, which can be very valuable information. Like for us, we try to use it to track flood waves propagating from upstream. Some people use it to figure out how much a nation is withholding water in its dams upstream, because you can use that information to do a lot of things. So all these are coming out as well. And again, most of this data is actually free. It's freely available, with the caveat that you'd be surprised, most of the times you really have to be pretty skilled to be able to use or take advantage of this data. because the form that this data is, it's a little bit complicated, things like rate or backscatter or simple harmonic coefficient, which to a water manager like you and me doesn't mean anything, unless you tell me what amount it is or how high or low it is. So these have been a pathfinder, but they're now getting to a stage where routine operations are very feasible. And I think 2020 onwards, it will be very common. So no matter how we look at it, I think for a lot of the regions, especially outside the U.S., the developed country, we do have a handle on how much water will we have, where, and when. Of course, the caveats are there's uncertainty, as there is with any way of measurement. And the scale is an issue. You won't always get it at the scale you're interested in. So I think the more important question is, how do we make ourselves ready for this situation? This is really a big data thing, or this even could be a tsunami, because these previous missions that I told you about, each of these will be streaming in a terabyte or more of data a day. And the current forecast that I have seen is if you put all the water measuring satellites, by 2020, we'll be getting at least 20 terabytes a day of data. And I think to most of my computer science colleagues, that probably qualifies as a big data problem. So the question is, how do we, go from there and empower the individual or an agency so that he or she won't really have to depend on us, experts, and really can have this access, and make decisions in the form of knowledge that is really useful. So that's the question that I'll kind of leave you with, and I hope we get some questions on it and hear some thoughts. But I will just leave with a couple of points that some of us are trying to work on. One is this data accessibility problem. It should be addressed in such a way that it allows use independently. I think we've come a long way, at least with satellite water data. If you look back like 15 years ago, like when I was in grad school, I really had to go ask or beg or plead with a student colleague of mine, hey, can you process that data for me? I need to use it for this. Now, a lot of these data portals, a lot of these missions provide tools that empower you where you don't have to depend on somebody else. I can go extract the data in the way I want, use it the way I want in the models. And in fact, we're doing it, a lot of it now, even in operational modeling and forecasting. Second thing, I think we should keep in mind the economics of it. If we are to judge our success of what we do by how redundant we make ourselves, especially in academia, which should not really require any kind of situation where the world is always dependent on us for what we do. Our business, in many cases, should be to get out of business by making sure that the innovations get taken over by the excellent, private sector entrepreneurship world where it's kind of in good shape. So it should not require very costly training, like you have to read lots of manuals. Although I think, Kristen's, the manual translation, the data language translation could come in pretty handy, and we might use that at some point. Like if we have to sell or somehow promote a certain satellite data mission to, say, Chile or Peru. I think probably use multiple ways of conveying the information. I'm just throwing out audiovisual. It should be highly intuitive, at least to get started. Sometimes we can make the simplest things unnecessarily complicated. And what I mean by intuitive is things that are kind of universal. So in this room, the exit signs that I see are written in English alphabets, but many places you will see a running sign, which, even my mom or my cousin who speaks a different language could understand, or the men's room and the ladies' room, those are signs. And there's many such, languages that are very intuitive that people really get for the common people. You don't really have to tell them what the simple harmonic coefficient is to Farmer Joe, because he really wouldn't be able to use it to make any empowering decisions. And definitely based on general rules of human cognition, and this is one area that many of us are not experts of, so we try to work with a lot of our computer science colleagues who do a lot of human-machine interfacing to see how humans respond to certain type of design that you have. So I'll leave you with this thought on, how do we get ourselves ready for this big data situation that's coming up from another platform called In Space, where at least 20 terabytes of data a day on water should be available to us reasonably freely of cost. And how do we use it, harness it, to create a higher level of empowerment from the individual to an agency to a nation? So thank you very much, and I'll leave you with a quote from my good colleague Larry Smith at UCLA, a Guggenheim Fellow, and he often says that, this was in his book, I think the Fourth Pole or something, the water crisis is about more than failing crops or unsanitary conditions. It's also about the information, or more precisely, the lack of it, for effective water management. And I hope all of us will think about it. How do we make the information more accessible? Thank you very much.
Thanks, Faisal. And that was really cool because actually at lunch I just read an article in Wired magazine about how they are releasing mini satellites, small satellites, swarms of satellites that are beaming this stuff back. And so dealing with that data is really pretty fascinating. So our next speaker is Eric Strecker, and I met Eric just a few moments ago, and the first thing that popped into our conversation was the Internet of Things, or as GE calls it, the Industrial Internet. So that'll tie into Eric's talk here as well. Eric is a PE and a principal engineer at Geosyntec Consultants. He's a water resources engineer and fisheries biologist with over 25 years of experience in stormwater and watershed management. He's conducted major applied research studies of stormwater for the U.S. EPA, U.S. FHWA, Water Environmental Federation, and the National Cooperative Highway Research Program, as well as numerous watershed and stormwater evaluation studies around the western United States. He is a principal investigator for the International BMP Database Project, and he's been the principal in charge of numerous projects that have deployed OptiRTC applications for real-time monitoring. Thanks, Eric.
Thank you. So a little more introduction. It was about 30 years ago this summer. I was a student at Moore Hall at University of Washington. So it's good to be back up here in the Northwest. So I'm going to talk about big data, little water, and making green work smarter and harder. And actually, I'm going to amend the title. It's a little or lots of water, and Christine stole that from me. No, I'm just kidding, but used that earlier. So I'm going to get into a little bit about flood control. So some key points are, typically in stormwater management, we apply passive controls. That is, we put an outlet in, we size a detention so big, put a passive outlet in, and then walk away and hope it works right. And we'll do a lot of work to try to make sure it does that. But what I'm going to talk about is the ability to actually take any information from the cloud or internet together with any local data and make decisions about when to open and close a valve. And turn our systems into smart systems. So you could do that for flood control, water quality enhancement, stream erosion control, as well as water supply augmentation. And the technology is cheap. Essentially, if you look at the cost of building new storage versus retrofitting a HIG, and HIG is a term that means hole in ground, or an above ground tank, that's what this is about. So some challenges with green infrastructure. There's a lot of emphasis on the use of green infrastructure to try to reduce our urban wet weather problems, be it CSOs or stormwater. And the problem is typically the green is going to be full by the time that really big event comes along. And that's the challenge that we have. And so it makes it difficult for green infrastructure. And then another challenge we have is that rainwater harvesting and wet weather management can have some pretty competing goals. For rainwater harvesting and use, we want to keep the tanks full and then use it for irrigation, versus stormwater, we might want to have the tanks empty before the storm arrives, and if we make a wrong call, we don't have our water anymore. So in 2009, on the 28th of April, an 80-degree day, I visited EPA, the Reagan building at EPA headquarters, and they had 6 1,000-gallon tanks sitting in the basement empty. And they hadn't actually turned them on yet because they had no demand for the irrigation water at that early part of the year. And so it made me think, here's some infrastructure that is pretty lazy. It's not working very hard. And it actually said here it takes about 9 to 10 days to drain the tanks when they're full and use it for irrigation.
And so it made me think there's probably some other ways that we could operate this tank and get more benefit out of it. So what I'm going to talk about now is a technology, we call it OptiRTC, and what is it? So basically it's a cloud-based suite of tools and computing services that together with local instrumentation provides automated real-time control, data acquisition, and data management solutions for a wide range of civil and environmental engineering applications. I'm going to focus on the water ones today, but we've used it at landfill, managing landfill gas systems as another example. So it's a distributed real-time monitoring, so it's hardware agnostic. We can take any kind of a sensor, as long as it has a signal, and take it into our system. It seamlessly integrates data from agencies like NOAA or USGS, quantitative precipitation forecasts or flow data. And then up on the cloud, you can use it actually to inform model runs and run model runs to help make decisions. It also has web-based visualization tools built into it, so any internet-connected device, you can take a look at what's happening with your system. You can also you can push a button and open the valve if you want to, if you set it up that way. And you can add, start with one site up to millions, so you can get up to the big data side of things. So this is just a little overview of the platform. I'm hoping, there we go. So in the center is the decision space. This is all run on Microsoft Azure, which we heard about a little bit earlier. So in essence, the way this system is set up is out at the site. We have an I/O bridge, which is the gateway to the internet. Could be connected up to a cellular telephone or hardwired, or a local internet, or if you have that. And then from that, we can take data in from sensors, so be it a depth gauge, a flow gauge, cameras, whatever you want to use. We can have control hardware out there, like valves, pumps, whatever you wanted to have there. And then we can gather any data we want from the internet, say quantitative precipitation forecasts from NOAA, and the chance it's going to rain and what depths we're expecting over the next short time horizon. Then from that, this is just showing a little configuration of the dashboard. You can send alerts out, so if you have a flood, for example, or equipment malfunction, whatever it is, it can go out and send alerts or emails and communicate via that way. So we have about 50 sites now where we've installed that. I'm going to just go through a couple of examples, but just to highlight one that's very effective in St. Joe, Missouri. There's a wetland complex. We actually drop it down about 2 feet prior to a forecasted combined sewer overflow event, and this wetland complex is within the combined sewer system. We make a tremendous amount of storage available to help prevent or reduce the combined sewer overflow that occurs. So again, this is a little rendering of the tanks at EPA's, and this is actually part of the visualization package where we'll go ahead and draw in the tank status, so it becomes, you can just look at it and say, oh, the tanks are full, versus look at some less friendly chart. So again, what we're doing in the headquarters is we use a precipitation forecast to decide when to hold or release stored water. So now I've put these tanks to work all year long. I can fill them up during the winter prior to an event coming on. I can then discharge them post-event, and then help reduce the contributions to the wet weather issues in the Washington, D.C. area. So this is an example site in Washington County with Clean Water Services in the Hillsborough area. There's about 120 acre catchment, that drains down through a couple of ponds here. I'm just going to narrow into it. This is the lower pond, is the one we retrofitted. The retrofit was simply going in and changing the outlet structure and installing the equipment. So our goals for the project was to improve the flow control functions of that. Prior to the retrofit, it was basically a little wet pond, did a little peak shaving after that. We estimated it controlled about 30% of the runoff in meeting the objectives for water quality control. And so we wanted to improve the functions of that, both the flow control and dealing with stream erosion, as well as water quality. And the Clean Water Services wanted to pilot this with the idea that maybe they extend it out and try to retrofit other infrastructure that's out there. So what we were doing, well, we have this storage volume that we could then make available in the pond. If we discharge the water prior to the event coming in, we now have significant storage made available to fill it back up. So this is just the equipment. Here's the outlet structure. This is the box with the equipment in it. It's all run by solar. A cellular telephone goes out. Excuse me. And this one has, this one here has the actuated valve within it. This is just showing the equipment that's out there. One thing we did learn the hard way a little bit is there's a little less sun in the Pacific Northwest than other parts of the country. And so these are two very large lead-acid batteries. We had to upgrade our solar panels as well as the batteries. So the cost of the system was about $21,000 for the equipment. And now the strategies we're using at that pond is to shift the discharge out of the wet weather window to the extent possible. So we try to control the discharge so that we just release the right amount and then fill it back up again without it overflowing. Of course, you know, weather forecasts aren't perfect, so sometimes it does overflow and sometimes it may not fill up completely. So again, we're trying to maximize the water quality pool and then get the base flow through there like I mentioned, and then also provide, if power fails or anything else like that, a failure, the system automatically releases, so we're not causing a flood control issue, being the risk-adverse consultants that we are. So the logic, we take the 6, 12, and 18-hour precipitation forecasts and use those to estimate the runoff volume we think we're going to see, and then the pond actually starts, the valve starts reacting to that, pond starts discharging and keeps updating. If the forecast change, we might release some more or maybe hold it at that point. Again, depending on how the forecasts are changing. So this is an event, just to show you one particular event that happened in the spring here. We had about a little over an inch of rain. This is at the Portland Hillsborough Airport, so fairly, you know, within a few miles of the site. So this is going to be just a little series of pictures here. We actually put a camera on here. I said, let's get a camera out there too so we can actually take a look at it and make sure that the gauges are reading correctly. Plus, I thought maybe from a security standpoint it would be a good idea to do that too. So in essence, this is the quantitative, this is the chance that it's going to rain. It's over 70%. And then these are the volumes that we expect. We turn that into, let's start changing the pond. So I'm just going to show a series of pictures here. We've now moved to this level of time where it's seeing the rain coming in within this time period. It starts dropping the pond. Again, it drops the pond a little more because the forecast has changed. Now it's starting to fill up with some rain. This is nighttime. Here it is filling up some more. And then at the end of the event, we have a near full pond. And that's how the system operated. So again, we kept the wet weather runoff out of the major runoff side of things. We also maximized the amount of wet pond water for water quality. So result downstream is the stream saw less runoff during the erosional parts, potentially erosional parts of that storm event. There's the last picture. So some other project types that one could use this for is, in essence, rainwater harvesting systems, similar to the EPA example that I just gave you, but turning those into smarter systems and using them for distributed storage. You could put them on green and blue roofs. You could actually choose to hold water on a roof and try to use that as a storage technique to prevent CSOs. We have an example where we've done a controlled under-drain on a bioretention system. There we want to try to maximize infiltration. Small drizzly event, hold the water up more. Big event, process more water through the under-drain. And I won't read through all of those, but I do think a big one here is retrofitting flood control basins and putting them to work a little bit more. So here's just again example of some of the windows. You can see a storm event coming into the East Coast. And so again, you know, systems start reacting. This is actually a green roof that we're managing at SAP headquarters on the East Coast of Pennsylvania. So this is here we're doing soil moisture probes, deciding when to irrigate or not based upon both the soil moisture conditions as well as the expected rainfall. This is the controlled bioretention. So essentially putting a little valve into this system, and then we change how water moves through that system and maximize its benefit. This is some work we're doing for the DC Fire Department, where we've retrofitted some firehouses, and in essence coming up with a little modular type system that one could go in and plop in at the firehouse. So again, taking runoff from the roof and putting it into a tank. In this case, I think they're using it for washing of the fire trucks, which they tend to do all year round. So it's a good source of a use of the water. So this again is showing the visualization about how full the tank is. It's available online. And this just is an actual picture of one of the systems. We actually put a green roof on the tank too, so it's green all over. This is a system at a housing project in St. Louis, Missouri. This is actually the cistern inside here, so here's a kind of a cutaway of what it looks like. And one of the lessons we learned from this was the system was actually an awesome construction QA/QC. We found out the tank was actually slowly discharging, and we found out one of the pipes had not been hooked up correctly. A lot of times we'd go out and put these passive stormwater controls in place, and we would never know it. So again, it becomes a good way to look for both the construction QA/QC as well as long-term maintenance. So I'm going to wrap up with a theme is we need to put our HIGs to work. Right now they're pretty lazy. We have a lot of peak shaving basins out there that are only operating about once every 25 years, or maybe 2 years to 25 years, but they're not working very often. So I think we need to get them to work. And how can we do that? We can instrument them with a control valve, be as conservative as you want with the flood control algorithm, because I can tell you that flood control people are not the most accepting folks sometimes of any more additional risk. But you could be as conservative as you want with the algorithms, and we can put a lot of these holes in the ground that are out there not working very hard and put them to work for water quality as well as flood control. And I would argue that just having a knowledge of the status of the pond would probably be better in terms of risk aversion on our flood control side than not having it instrumented and using it in the traditional way that it's used. And it's cheap. So when we get into thinking about how we're going to deal with wet weather issues in our nation, I think taking advantage of the existing infrastructure and making it work harder makes a ton of sense. So with that, I'm finished.
Thanks, Eric. And our last speaker is Dr. Joan Wu. She's a professor at Washington State University. I was talking to Joan just a little bit before lunch, and she described the challenges of connecting with 8th graders when you're making a pitch and a presentation. So I hope none of you are feeling like 8th graders in here right now, but part of that, there's a real call to us as well, is connecting with this next generation and talking about what we're doing and how we're connecting and giving paper and the handouts. And our old mode of business is just not going to work with Generation Z and beyond. So that's one of my passions, is how are we really using technology to connect to that next generation, the stewards that are coming out. So Dr. Wu received her BS in geology and MS in hydrology from Tongji University in Shanghai. She's also received another MS in mathematics from WSU and her PhD in agricultural engineering from the Ohio State University in Columbia. Since 1998, Dr. Wu has been an assistant, an associate, and a professor in the Department of Biological Systems Engineering at WSU. Prior to joining WSU, she was an assistant professor at UC Riverside. Dr. Wu has collaborated extensively with USDA and U.S. Forest Service in continuous development of the Watershed Erosion Prediction Project model and its technical responsibilities for all the new WEP releases. WEP is one of the most widely used water erosion prediction technologies for watershed assessment and management in the U.S. worldwide. So, Dr. Wu.
Well, I'm very grateful to the organization committee for the invitation to this conference, and thank you, Scott, for the introduction. I'm going to share with you a map to begin. This is a land use change. As many of you have probably witnessed, in the past few decades, the Puget Sound region has experienced the rapid growth and development. This faster development, unfortunately, has also led to adverse serious impact on the Puget Sound ecosystem. The map shows land use change over 1 decade only, and this is from 2001 to 2011. As you can probably see, the legend says that the pink-colored regions or areas are those that were originally forest lands, and later they were converted to some other land use. The orange color was agricultural lands, and now there's something else. Basically, a rough statistic shows that for these 10 years, upwards 4,000 acres of agricultural lands were lost to urban development, and about more than 16,000 acres were actually converted to use from forest lands to commercial or residential. And this is very startling to me because the development wasn't centered about Seattle or Tacoma. Rather, it was further south to Olympia and further north beyond Bellingham. Now, among the numerous environmental issues we're facing are legacy toxic chemical contamination, shoreline development and loss of habitat, and most startling, eutrophication due to excessive loading of phosphorus and other nutrients. At WSU, a long-term research goal of ours is to perform hydrological assessment for land and water resources management, restoration, and protection. Here I was given only about 5 slides and 12 minutes, and so I would only share one study that's more used as an example to show data, whether they are big or small, little or few, and what about water. But I'm going to focus on water quality. So this study aims at modeling nutrients transport and more specifically phosphorus loading using hydrological modeling as the effective tool. Now, the motivation was built on our increasing awareness of research done for urbanizing or urbanized regions. A 1999 synthesis study by the USGS based on national water quality data assessment pointed out that the culprit for surface water pollution is no longer agricultural production. Rather, ag production remains the leading source for surface water, stream water in particular. However, the wastewater treatment facilities are the leading sources for estuarine pollution. Locally, we do not have much data, or I should say the literature is limited, yet global studies continue to provide data demonstrating excessive phosphorus loading in surface runoff from non-agricultural landscapes as well as gardens. You might know that Washington State has joined 15 other states to ban the use of phosphate detergent. And also we joined other 12 states recently to ban or restrict the use of phosphorus fertilizer for long use. Other than exceptional cases, you no longer see these commercial fertilizers. However, in local stores, Home Depot or Lowe's, I think they very aggressively marketed the other forms of phosphate fertilizers, something called triple phosphate or superphosphate. So we continue to use those. Yet many gardeners do not know that phosphorus of phosphate is not the limiting. Basically, in Western Washington, this nutrient basically is not lacking. Okay. So what is our approach? We have a two-step approach to this problem. First of all, according to USDA and NRCS, we are adapting the nationally recommended P-index method. This method does consider two groups of factors. The first one is the transport factor. This includes erosion by water, runoff class, distance to stream, as well as flooding frequency. And it also considers site factors such as the soil P level based on soil test, as well as commercial and organic phosphorus fertilizer application rate and method. You might know that the way you use the fertilizer also determines the pollution potential, transport potential. Currently, NRCS in the Spokane office has given the users a worksheet. The worksheet for consulting firms is not really difficult to use. However, for any ordinary homeowners, gardeners, I think it's quite challenging, it's quite involved. So I think a very straightforward exercise for a graduate student would be to convert the worksheet into a GIS model. I think many of you are familiar with this abbreviation, Geographic Information System. Basically, these factors you can see can be manipulated any way you like. For Western Washington, where flooding frequency is predominant, meaning that every household can have a potential risk for flooding, you can basically add these factors together to come up with a risk rating. For Eastern Washington, though, the method is to multiply the factors, and you could also apply weights to different factors. Now, after all, these are examples my graduate student quickly put together. So by adding or multiplying the site and transport factors together, you have a final phosphorus risk rating. However, this rating is categorized very broadly as very high, high, medium, low, and none. With these five categories, I think city planners or regulatory personnel can readily see the so-called hot spots, or those areas where the phosphorus pollution potential is high. Yet it doesn't provide a quantitative assessment. Also, it doesn't provide with you the transport pathways. So the next step, we are going to use a more sophisticated, physically based modeling approach. As Scott mentioned, the WEP stands for Water Erosion Prediction Project. You might think I do not look awfully old, but I've spent all my career on this model, so it's much older than my own children. It is a computer program for simulating watershed hydrology and erosion. Initially developed, I think the first year it was developed was 1989. I came to the U.S. the next year attending one of the earlier developer group meetings. At that time, more than 100 scientists and researchers across the nation were gathering at West Lafayette, Indiana. That was among the earlier meetings to develop this model. The intention was to replace the universal soil loss equation with this more physically based approach. Later on, the main client of USDA ARS, which is NRCS, doesn't quite buy this product because they thought it's too complicated, uses too many parameters, and growers, farmers cannot afford. They don't have a powerful computer. But apparently they underestimated how fast the computing technology would advance. Well, partially thanks to Microsoft, I guess. Anyway, it's built on fundamentals of hydrology, plant science, hydraulics, erosion mechanics, and it does simulate hydrologic and erosion impacts of varying topographic, climatic, soil, geology, and management conditions. What sets this model different from our European counterpart, the so-called EuroSum, is that we also have a very comprehensive U.S. database. You could never underestimate how powerful when you have such a database. This dramatically eases the use of such a model. I grew up in a communist regime, which is China. There, as Friso said, that sharing water is very hard. Sharing water information is nearly impossible. In August, I went back to China for a visit and also business collaboration or research collaboration. I was told that even 30-meter DEM, this is elevation digital model, basically topographic information, is national secret, whereas Google already gives you 50-meter resolution freely to anyone. So I think such cultural, political difference also sets roadblocks to advancement of science and research for sure. The way we use this model is via an interface. This was also proudly developed by Washington State University in collaboration with USDA and Forest Service. You could freely download the interface from the Purdue web server, which is National Solar Research Lab. A user basically needs a computer, keyboard, and web browser. All the spatial data that are managed by national or federal governments can be automatically retrieved. This includes USGS 30-meter DEM, USGS National land use land cover, as well as the NRCS Circle soil data. What is not listed here, but it's the most important thing, is the driving force, the climate data. This is also readily available. It was already embedded in the original web model. More than 8,000 NOAA weather stations, together with the long-term weather data, are all included. If you have a basic training in hydrology, working in the private industry, or just as general public, you're interested in knowing what's going on. If you have a land use change in your hometown, you can click buttons. I just thought, how can we convince kids, instead of playing video games, and playing this model? Okay, so this is the interface. We were commissioned initially by U.S. Army Corps of Engineers to develop it for the Great Lakes region, and later we also received the funding from California and U.S. Forest Service to develop another interface for Lake Tahoe. And eventually this was expanded to the whole nation. So nowadays it's basically for any state. 2 days ago, last week, I was giving a talk to 8th graders, a math conference at the Clover Park Technology College. And so these 8th graders were very fascinated by the pictures. But when I pulled out a pamphlet, which is the 2013 Tacoma Annual Water Quality Report, was asking them, what do you think about water quality? They were blank. They had a very blank expression. Then I asked them, anything you could think of, what are the things that make you feel not like drinking the water? Eventually, some kids said, maybe the color or the odor. That's wonderful. These are indices. Yet none of the kids, I taught 4 classes altogether, I think 120 kids. None of them gave me heavy metal or a pesticide or fertilizer, none, and nutrient, whatever. I was just thinking, we are trying to promote a STEM education in our high school, elementary, or college students, yet our kids are very fascinated by iPhone, iPad, iPod, whatever, this, that, yet they are not quite knowing a few water quality indices. So we have our Microsoft expert here. How can you develop the so-called apps so that kids are more aware of these issues? That would be wonderful. So the next more the data challenges where hydrological modelers face each and every day. I was very amused by the title of this panel. In the beginning, I thought big data. All my students, all of them complained to me, oh, I don't have enough data. What do I do with this missing data? So being a hydrologist, you grew from an infant stage to more mature stage by being able to handle missing data. I think one of our qualifications is we can come up with a way to make up for the missing data, yet we can be defensible. So a colleague wouldn't say, oh, why don't you try something else? I think that's a better way. So these are the difficulties I can share with you. Number one is georeferencing the point and non-point sources. I checked the Agriculture Economic Service database. They gave you county by county, year by year data of the crops you grow, but they would never say so-and-so farms would use these many tons of fertilizers or pesticides. And so without such point sources, exact location, how am I going to depict to you the pathways of transport of pollutants? There is not much we can do. I was also told that the organic farmers are more willing to share with you their farming information because they don't use much. They believe they are better steward, but conventional farmers probably would not welcome you to do soil testing or give you any information. Also, we actually lack dramatically the water quality data from USGS gauging records. We have the stream flow, but we do not have a lot of chemical concentration data. And of course, we also lack site-specific hydraulic properties. And above all these data have uncertainties. Very rarely we address uncertainty issues as if the results from any hydrologic studies are cast in stone or fixed. They are not. They have associated with them a lot of uncertainties and errors. With that, I think I conclude my talk. Thank you.